think for a moment about a really clear night sky. I mean, not just a few stars, but that incredible, overwhelming scatter of light across, that deep black background.
Yeah, like diamond dust.
Exactly. Each tiny point is a sun, maybe like ours, incredibly distant. And those faint smudges, whole galaxies, it's breathtaking.
It really is. And looking up like that, well, it sparks something fundamental in us, doesn't
A
it?
need to understand, I think,
Yeah.
to make sense of it all, to map it.
Precisely. And that's what we're diving into today on the All Sorts podcast.
Welcome, everyone. Today, we're charting a course through astronomical mapping, the art and science of sketching out the cosmos.
And what's really amazing is just the scale of it. We're not just listing stars, we're trying to build a framework to understand, well, everything out there.
So for this deep dive, we've looked at sources covering the basics of how mapping works, coordinate systems.
Right, astronomical surveys, even the history of how we've drawn the heavens over centuries.
Absolutely. And our goal today isn't to drown you in data, okay? It's more like a guided tour.
Yeah.
We want to shed light on how astronomers take this vastness and make it understandable.
Yeah, gaining a bit of cosmic perspective. And hopefully you'll find some surprising things about how meticulous this whole process is.
So let's start right there. Why even bother? Why map the universe? What's the driving force?
Well, fundamentally, it's about that deep curiosity, isn't it? Understanding our place. But practically, astronomical mapping is about charting the exact positions and the properties, what things are of stars, galaxies, quasars, all that stuff.
Okay.
But it's more than just making a big cosmic address list. Because light takes time to travel, we're also looking back in time.
Right. So seeing a distant galaxy is seeing it as it was billions of years ago.
Exactly. It's a journey through time and space. And the data comes from everywhere, telescopes on the ground, things like Hubble up in space, giving us super clear views. And even radio telescopes, listening to wavelengths we can't see.
So it's like being a cosmic historian and a geographer all at once. What kind of information are they actually collecting?
Oh, a whole range.
Okay.
We need the precise location, obviously. Then there's brightness, but not just overall brightness in different colors, different wavelengths of light.
Okay.
We look at chemical composition, what things are made of by analyzing their light. And crucially, their movement. Are they moving towards us, away from us, orbiting something else?
Each piece of that sounds like a clue.
It is a clue to a much bigger picture. Understanding how galaxies are distributed, for instance, wasn't just about locations. It eventually helped confirm the existence of dark matter.
Which is still pretty mind-bending stuff.
Absolutely.
Okay, so we get the why, but the how. How do you even start mapping something that huge and complex? What are the basic tools?
Right. There are a few key pillars, you could say. Let's start with astrometry.
Astrometry, okay.
This is all about super precise measurements.
Yeah.
Where things are in the sky and how they're moving. And the accuracy we can achieve now is just incredible, partly thanks to techniques like interferometry. We can talk more about that.
Okay.
A great example is the Gaia mission from the European Space Agency. Think of it like it's taking a census.
A census of stars?
Yeah, of over 1 billion stars in our Milky Way. Gaia is meticulously measuring their positions, their tiny movements over time, their distances.
1 billion stars? That's
Yeah.
hard to even grasp.
It is, and that level of precision lets us map out the structure of our galaxy, see how it formed, even predict how stars will move in the future.
So tracking those tiny shifts tells us about the big picture, like how the whole galaxy rotates.
Exactly that. It's like watching individual dancers to understand the choreography of the entire cosmic ballet. It reveals the dynamics.
Okay, so astrometry nails down the where and how fast. What's next in the toolkit?
Next up is photometry. This is about measuring brightness.
Just how bright a star looks.
Well, yes, but it's more nuanced. We measure brightness across different specific wavelengths or colors of light. And analyzing that tells us a surprising amount.
Like what?
Like a star's surface temperature. Comparing brightness in, say, blue light versus red light is a key indicator. The overall intensity helps estimate its size and distance, too.
Ah, I see.
So photometry is essential for classifying stars into different types, finding stars whose brightness changes over time, variable stars, which can be really interesting, and even studying whole galaxies by looking at the combined light of all their stars.
So the light itself, its color and intensity, carries all this information. It's like a code.
It really is. Photometry is like our cosmic thermometer and measuring tape, all rolled into one.
Fascinating. Okay, so we've got position, movement, brightness. What if we dig deeper into the light itself? Break it down. That's spectroscopy, right?
You got it. Spectroscopy is where we take the light from an object and spread it out into its spectrum like a rainbow. But it's not usually a smooth rainbow. You see dark or bright lines interrupting it at very specific wavelengths.
Fingerprints.
Exactly, chemical fingerprints. Each element absorbs or emits light at unique wavelengths. So by looking at these spectral lines, we can tell exactly what a star or a galaxy is made of.
Wow.
And not just that. The lines also tell us about temperature, pressure, and even velocity. If the lines are shifted towards the red end of the spectrum that's redshift, the object is moving away from us. Shifted towards the blue shift, it's moving towards us.
And that's the Doppler effect, like with sound waves.
Precisely. And, measuring the redshift of distant galaxies was some of the first really strong evidence that the universe is expanding, a cornerstone of the Big Bang theory.
That's incredible. So just by carefully looking at light, we know where something is, how bright it is, what it's made of, and how it's moving.
Yep. Spectroscopy is absolutely vital. We use it to understand how stars evolve, to check the composition of atmospheres around planets orbiting other stars, exoplanets.
Looking for signs of life?
Potentially, yes. And also for studying how galaxies rotate, how the stars inside them are moving around. It's a powerhouse technique.
We've mostly talked about visible light, but you mentioned radio telescopes earlier. What do they add to the picture?
Right, radio astronomy opens up a whole different window on the universe. It detects radio waves, which are much longer wavelengths than visible light.
And that lets us see things we wouldn't otherwise.
Exactly. Things that are too cool to shine brightly in visible light, or hidden behind thick clouds of cosmic dust, or things that just naturally emit strongly in radio waves.
Like what kind of things?
Well, pulsars, those are rapidly spinning neutron stars, the remnants of massive stars. Quasars, incredibly energetic cores of distant galaxies, and also the huge cold clouds of gas and dust between stars, the interstellar medium.
Where new stars are born.
That's right, the stellar nurseries. And just like with light, we can use radio interferometry.
Okay, you've mentioned interferometry a couple of times now for both light and radio. How does that actually work?
It's a really clever trick. Instead of building one gigantic telescope, which can be impractical or impossible, you use multiple smaller telescopes spread out over a distance.
Right.
You combine the signals they receive electronically. By doing this, you effectively synthesize a telescope as large as the distance between the farthest individual dishes or mirrors.
So you get the resolution, the detail-seeing ability of a much larger instrument.
Exactly. The further apart the telescopes, the finer the detail you can resolve. It's like having much sharper vision. It works across many wavelengths, from radio right through to visible light, letting us get incredibly detailed images of very distant or small objects.
Okay, that makes sense. So we've got these amazing techniques: astrometry, photometry, spectroscopy, radio astronomy, interferometry, gathering all this data. How does it all come together into a map?
That's where computation comes in. You take all this diverse data, feed it into sophisticated computer algorithms, and they build comprehensive models of the cosmos. And crucially, these aren't static pictures. They're dynamic.
Dynamic meaning they show how things change.
Yes, and how things are structured in 3D space. These models help us understand the universe's large-scale structure. The fact that galaxies aren't just randomly scattered.
The cosmic web.
The cosmic web, exactly, with its filaments and clusters and these vast empty regions called voids. Big surveys, like the Sloan Digital Sky Survey SDSS, have been absolutely key in mapping this out. They've measured millions of galaxies.
So the maps reveal the universe's architecture.
They do.
Yeah.
And they also let us track evolution over cosmic time, how stars live and die, how galaxies form and merge, how the universe itself expands and changes.
And does this help find new things?
Definitely. These detailed maps are essential guides for searching for new planets around other stars, exoplanets, or finding other interesting objects that deserve a closer look with bigger telescopes.
It's not just the distant universe either, is it? This applies to our own solar system, too.
Oh, absolutely. Mapping the precise orbits of planets, asteroids, comets in our own backyard is fundamental. It helps us understand how the solar system formed.
And it keeps us safe.
That's a big part of it, yes. Tracking near-Earth objects, asteroids that might pose a risk. There are dedicated projects constantly scanning the sky for potentially hazardous objects. Things like SpaceGuard, Etelis, NeoStel. Their job is planetary defense.
Right, crucial work. Now, when we talk about these maps, whether old star charts or modern digital ones, how do astronomers actually specify where something is? We need coordinates, like on Earth, right?
Exactly. We need astronomical coordinate systems. Just like latitude and longitude pinpoint a spot on Earth, these systems define locations on the celestial sphere, that imaginary sphere surrounding Earth onto which all stars appear to be projected.
Okay.
All these systems basically work by defining two things: a fundamental plane, like the equator on Earth, which divides the sky in half, and a primary direction on that plane, which is your starting point for measuring angles, like the prime meridian.
Makes sense. So what are some common systems?
Well, for an observer right here on Earth, the most intuitive one is the horizontal system. Its fundamental plane is your local horizon.
The line where the sky meets the ground?
Right. And the coordinates are altitude, how high an object is above the horizon, and azimuth, its direction around the horizon, usually measured from north through east. Super useful for pointing your telescope right now from your location.
Okay, that's very observer-dependent, though. What about more universal maps?
For that, we mostly use the equatorial coordinate system. Its fundamental plane is the celestial equator, just Earth's equator projected out into space.
Got it.
The coordinates here are declination, which is like latitude, measuring north or south of the celestial equator,
Okay.
and right ascension, which is like longitude, measured eastward along the celestial equator, usually in hours, minutes, and seconds. This system gives us a map of the sky that's basically the same for everyone on Earth, and it's what most star charts and telescope mounts use.
I've seen references like J2000. What's that about?
Yes. That refers to the epoch. Because Earth's axis wobbles slightly over long periods, it's called precession,
Yeah.
the coordinate grid slowly shifts against the background stars. So astronomers agree on a standard reference point in time. B1950 was an older standard, based on the position around the year 1950. J2000 is the current standard, based on noon on January 1st, 2000. It just ensures everyone's using the same grid.
Okay, so horizontal for local viewing, equatorial for general maps. Any others we should know about?
Yeah, a few others are important for specific things. There's the ecliptic system, which uses the plane of Earth's orbit around the sun, the ecliptic as its base. That's really useful for tracking the sun, moon, and planets because they roughly follow that plane in the sky.
Makes sense.
Then there's the galactic coordinate system. Its fundamental plane is the disk of our own Milky Way galaxy. Galactic latitude and longitude are perfect for studying the structure of our galaxy, seeing how stars and gas clouds are distributed within it.
And you mentioned supergalactic earlier.
Right. The supergalactic system is for even larger scales. It uses a plane defined by the distribution of nearby galaxy clusters, the local supercluster. It helps us understand the arrangement of galaxies in our cosmic neighborhood.
It's amazing how many different frameworks are needed, each offering a unique perspective on the cosmos. Let's switch gears a bit and look back. Celestial mapping isn't new, is it? This goes way back.
Oh, absolutely. Celestial cartography mapping stars and constellations is ancient. Babylonians, Egyptians, Greeks, Chinese civilizations, they all created star charts thousands of years ago.
And not just out of curiosity, right? They were practical.
Very practical. For navigation, finding your way on land and sea, for agriculture tracking seasons by the stars, and also deeply tied into their religious beliefs and cosmology. These weren't just scientific tools, they were cultural artifacts. Then, during the Islamic Golden Age, astronomers in the Middle East made huge leaps. They created incredibly detailed star catalogs and atlases, much more accurate than what came before, and they heavily influenced European astronomy later on.
And the Renaissance.
That saw real flowering of the art form. Maps became more accurate, but also incredibly artistic. You see things like Andreas Cellarius's Harmonia Macrocosmica in the 17th century, scientifically informative, but also just stunningly beautiful, with mythological illustrations woven in.
Works of art as much as science.
Definitely. Later, in the Age of Enlightenment, people like Hevelius and Flamsteed produced even more precise atlases, incorporating observations made with early telescopes.
Ah, the telescope. That must have been a game changer.
Huge. Suddenly you could see vastly more stars, fainter objects, details never imagined before. And then, much later, came the digital revolution.
Right. Everything changed again.
Completely. Now we have online databases, amazing software like Stellarium, which is free and open source, by the way. It gives you a realistic 3D sky on your computer. You can zoom in on galaxies, see coordinate grids, constellation art. It's incredible.
So we've gone from hand-drawn scrolls to interactive simulations. But those old maps are still valued.
Oh, for sure. Yeah. Antique star charts are highly collectible for their history and artistry. Reproductions are popular, too. And modern printed charts are still essential for amateur astronomers out with their telescopes.
You know, it's worth mentioning Albrecht Dürer's map from 1515.
Ah, yes. a real landmark. It was a collaboration, and thanks to the printing press, it was the first star chart to be widely distributed.
And it showed all the constellations relative to each other with coordinates.
That's right, a big step forward. And interestingly, around that time, with texts coming from the Arab world after Constantinople fell, many stars on European maps ended up with Arabic names, even within the classical Greek and Roman constellations.
A real mixing of traditions.
Yeah. There were even brief attempts later to sort of Christianize the constellations, replace the old myths with biblical figures, but that didn't really catch on.
Fascinating history. Okay, so we've talked about individual maps and techniques, but modern astronomy relies heavily on these massive projects, right? Astronomical surveys.
Exactly. Surveys are fundamental. A survey is basically a systematic mapping of a region of the sky, sometimes the entire sky, without having one specific target in mind beforehand.
Like taking a wide-angle photo instead of zooming in on one thing?
Sort of, yes. Or it could be observing thousands of objects of the same type, like galaxies or quasars, across a large area. They often focus on one part of the electromagnetic spectrum, like optical light or infrared or radio. But multi-wavelength surveys are also common now.
And why are these so valuable?
Several reasons. They create huge catalogs of objects, which are invaluable resources for all astronomers. They allow for statistical studies of large populations without the bias you get from just picking interesting objects to look at. Sometimes, if you need data on a specific star or galaxy, you find it's already been observed and cataloged by a survey, which saves a lot of time and effort.
Like a library of the
A
sky.
good analogy. And because surveys often observe the same patches of sky repeatedly over time.
You can see things that change or move.
Precisely. That's how we find asteroids and comets. Compare images taken days or weeks apart, and you spot the moving dot. That's crucial for finding those potentially hazardous near-Earth objects we talked about.
Right, the planetary defense aspect again.
Yes. And you can also spot transient events, things that flare up or fade away, like variable stars or even supernovae, by comparing survey images.
It sounds like surveys underpin a huge amount of modern astrophysics. Can you give some examples? Across different wavelengths.
Sure. In optical light, historically you had things like Hipparchus's early catalog, the Bonner-Dirch-Mustrung, the astrographic catalog. The Henry Draper catalog was groundbreaking for classifying stars by their spectra.
Okay.
More recently, the Sloan Digital Sky Survey, SDSS, has been hugely influential, mapping millions of objects. Gaia, as we mentioned, is revolutionizing astrometry. The Zwicky Transient Facility, ZTF, is great at catching things that change quickly. And the upcoming Vera C. Rubin Observatory is expected to be transformative.
And beyond visible light.
In infrared, surveys like IRACE, 2MASS, and WISE have mapped the cooler side of the universe. Dust clouds, cool stars. Future missions like Euclid and the Nancy Grace Roman Space Telescope will push this further.
Radio.
Classic radio surveys include the third Cambridge Catalog, 3C, the NVSS, FIRST. There are ongoing searches for pulsars like Pallofa. Even gamma rays have surveys, like the one by the Fermi Telescope.
And combining wavelengths.
Right, multi-wavelength surveys like Gamma, GOODS, Cosmos, CANDLES try to get data across as much of the spectrum as possible for the same patches of sky, giving a really complete picture of the objects within them.
It's truly awe-inspiring. The scale, the collaboration involved in these massive projects, often spanning decades and countries.
It really is. These surveys provide the bedrock data for so much of what we understand about the universe today.
So let's try to wrap this up. We've journeyed through the why and how of mapping the cosmos. We've looked at the core techniques: astrometry for position and motion,
Photometry for brightness and temperature,
spectroscopy for composition and velocity,
radio astronomy for the invisible universe, and interferometry for super sharp vision.
We navigated the coordinate systems astronomers use to pinpoint everything, from our local horizon to the galactic plane.
We touched on the amazing history, from ancient star charts to digital skies.
And we highlighted just how crucial these large-scale astronomical surveys are for building our cosmic knowledge base.
And through it all, these maps, whether they're beautiful old drawings or complex modern databases, they all tell a story, don't they?
They do. A story of human curiosity, of our relentless drive to understand our place in this vast, incredible universe.
It's a quest that continues.
Absolutely. Which leads to a final thought. Technology never stands still. Telescopes get better, data analysis gets smarter. How will our maps of the cosmos change in the future? What completely new things might we discover? Are there whole new cosmic continents out there waiting for us? It really fires the imagination.
It does indeed. And just as those early map makers ventured into the unknown, here at the All Sorts Podcast, we love exploring uncharted intellectual territory.
And if this deep dive into cosmic cartography has sparked your curiosity, why not join our expedition? Please head over to YouTube, find the All Sorts Podcast, and hit like and subscribe. That way, you won't miss any of our future explorations.
And share this discussion with others who love to learn. Help us spread the knowledge. Don't forget, we have a whole back catalog of deep dives covering all sorts of fascinating topics waiting for you.
That's right. And for more interaction, updates, and behind-the-scenes stuff, follow the All Sorts Podcast on X, Instagram, and Threads.
Let's keep mapping the amazing landscape of human knowledge together.